The next couple lectures, we will talk about steady flow and steady flows, and how the vortices and how the vortices play a role in circulation, and how and vice versa. So let's just start a very quick review on what we have done so far. And to do that, uh, I want to start with the very simple discussion on what is steady versus unsteady. So what is a steady flow? Steady versus unsteady. Okay. So first of all, when we talk about a steady flow, we are talking about flow that's going to remain the same in position in respect to time. As an example, so for steady flow, you think about a fixed object and consider the following case. Let's suppose I have a fixed object in space. And let me change the colors quick. And I have a flow that comes like this. I have a flow that comes like this. And let's say that's happening at time. That's happening at time equal to time 1. Now at time 2, if I'm going to do this at time 2 and I evaluate my flow will be completely identical. So at time 1 and time 2, I have identical flows. So what you can see in this location is that the object, in this case, the object remains in the same position, in the same place and position. Okay? Now, for the case of unsteady flow, the following things happen. So now in this particular case, the particle path lines are different. Are different. Let me give you an example. Let's suppose I have an object. Now, this particular object, about time, it is actually rotating. So now, since it's rotating, my flow along this will maybe look something like this. That would be, let's say, at time equal to time 1. But time equal to time 2, since my object is rotating with time, it's the same object, identically the same object, but it's rotating, right? So in another rotation, now my flow is actually going to look like this. So you can see that my path lines are completely different at time 1 and time 2. That means that my flow is unsteady flow, is time dependent. Okay, and this, as an example, this unsteady flow is a consequence of a rotating object. Okay, the rotating object is the one that's responsible for that. Okay, now the second thing that I want to talk, and we kind of talked about this, but just want to quickly review what we talked before, is fluid lines and fluid particles and particle paths, sorry. So the first thing you want to talk is about fluid lines. Um, so fluid lines is nothing else than any continuous string of fluid particles. Is any it moves, something that moves with the flow. It cannot be broken. So let's consider the following case. Let's suppose I got an airfoil. This is an example. Okay, so I have an airfoil. So this is an airfoil. And across this airfoil, I'm going to have two lines here. Let's consider, in one case is line number 1. I got line number 2. And then I can have another fluid flow that actually looks like this. Okay, so these are different flow lines. This is number 3, this is number 2, and this is number 1. And what you can see is the particle is actually moving somewhere here that does this, and it's a small particle that's going along my path is actually doing this. The same particle is moving in different location, is moving in this direction. Okay, so this right here is what we call particle path. Okay, so these are fluid lines. Okay, and this you can see this is a fluid loop. Number 3 is a fluid loop because you can see starts here and just goes around this. These are fluid lines. These are particle lines. Actually moves along to the contour of my object. Okay, so there are a couple of other things that we discussed and we have talked about before. And I just want to just to capture a few things, and we can move beyond our previous subjects. And it's the concept of streamlines. We talked about streamlines. We know what streamlines are. First of all, streamlines are nothing else, a line everywhere tangent to the velocity vector. Okay, so if I have this case at every point where I have streamlines, the velocity vector is completely tangent. It's tangent at every point. Okay, these are tangent lines. And they never cross except they will never cross except at stagnation point. Okay. Number 3 for streamlines, they're not functions of the flow, but of my frame of reference. but my, and I'm going to put my, right, between quotes, frame of reference. Okay. Okay. So that's what we know about streamlines. And we talked last time that streamlines mathematically, we find them by taking the cross product of your small displacement ds with the velocity, and you set that equal to 0, right? So we did that last time. So another concept that we have and we keep in mind, and this is something probably new that we haven't talked about yet, is what we call stream surfaces. Okay, a stream surface. Now, if you think about a small, if I can just have a small surface there, and now think a surface, but the surface full of is flow lines, right? Actually, flow goes like this, but they will go across a surface that I decide this flat surface doesn't have to be flat, can be curved, like in this particular case, right? As you can see here, it's a surface. And here, what you're going to have here, you're going to have a flow that's actually happening across that surface. Okay, and think that this surface is actually going all the way, you know, it's a maybe it's something like this. Okay, okay, it's a surface, and you got a surface flow. So if I'm going to actually draw this, you could think that this is actually, if I can get this right, doing like this. It's actually doing like this, straight lines all the way across on the surface itself. Okay, and this right here is what we call a stream surface. Okay, this is what we're going to call right here a fixed curve. So a couple of things we can talk about stream surfaces. It is a surface. It's a surface everywhere tangent to the velocity vector. It's a surface made of all streamlines passing through a fixed curve in space. Made by all the streamlines passing through a fixed curve in space. Number 3, no flow through the stream surface. Okay. Number 4, stream surfaces two stream surfaces can intersect each other. So stream surfaces So an example of this, let's see how we draw this. So I'm going to draw this one in a different color so you can actually see the difference. So, and this is going to have a different flow. This is going to be a different stream surface. Okay, so the surfaces can intersect each other. Now, the another thing that we also have is what we call stream tubes. And all this is important for what we're going to be discussing today. Okay. In the case of a stream tube, I want you to think we got a huge tube that maybe is doing something like this. Okay, and on the opposite side then is a tube. And now in the tube, you're going to have flows, and the flows go like this, right? You have flows actually go along this. Let me get this right. And then you also have flows on the opposite side, right? They actually go around the tube. Okay, they just happen around the tube. So in this particular case, a stream surface rolled to form a tube. Okay, that's what it is. It's a surface that we can roll it so it just looks like a tube. It's a stream surface rolled so it forms a tube. And it's important to know there's no flow through the walls. Okay? Those are stream tubes. Now, we also have something we call stream functions, and we will talk more about this probably in 2 classes, but to get a little bit ahead of myself. Stream functions. This is nothing else a function, which is a constant. It's a function which is constant on a particular stream surface or stream tube. Okay. Okay. So what is the relationship between all of these? Okay. The relationship between streamlines stream surfaces, stream tubes, stream functions. Okay? So consider a case in which you have two concentric tubes, stream tubes. Okay, so this is tube number one. And then maybe you have another tube that goes on the outside, that concentric. So they are one inside the other. Okay, and then you can have two surfaces, okay, arbitrary surfaces, okay, and these are what we would call stream surfaces. This is what we would call stream tubes. Okay, and you can have a case like this. And what you're going to have here is, if I just, for the sake of this example, if I call this surface 1, and I call this surface 2, and I call this tube 1, and I call this tube 2, what you can see is, in this particular case, it takes two families of surfaces to locate a perpendicular stream in a three-dimensional flow. You can see that I'm going to have a perpendicular flow there. Somehow there's going to be a perpendicular flow. I'm going to show you this in the next slide. But it requires at least two families of these surfaces to do that. And that's the intersection of this. Okay, so let me write this down. It takes two families of surfaces to locate a particular streamline in a 3D flow. Okay. So what I'm actually trying to say is, let's consider this case, right? So you have a, see how I can draw this. So you have a streamline, and you have a surface that comes like this. You have a surface that, this is the second surface. Okay, and you can see that this surface is given by a function sigma 2, psi 2. This surface is given by a surface psi 1, and they're completely constant. Okay, they represent that one surface in 3 dimensions. And this right here is what we call the streamline. This is how these are related to each other. And you can see here, let me change the color here. And here you're going to have the velocity vector. Okay, remember the velocity vector is going to be tangent to this streamline. Then here in this location, in this particular location, I will have, because of this guy here, is the gradient. So I can have the gradient of this, of psi, is actually perpendicular to this surface, okay? And then to this particular surface, then I have another gradient that's perpendicular to that surface. So that's the gradient, okay? So what we can see here is, and you can see here that your velocity vector is going to be perpendicular to, to the gradient of psi 1, and also your velocity vector is going to be perpendicular to the gradient of psi 2. They will be completely perpendicular to each other. Okay, so so this is important to understand that these are not perpendicular to each other, by the way. This is perpendicular to the surface. This is perpendicular to this surface. Okay, that's the gradient. Um, and the gradient of a function, just as a review, okay, so if psi is actually a function of x, y, and z, then the gradient is defined as a vector, okay, that's partial of psi respect to x, partial of psi respect to y, partial of psi respect to z is a vector, okay, that has three components, but this has three components. That's how we define that. So, and to continue this discussion in the next slide, what you're going to have is that the divergence of V, that's nothing else than the divergence of the gradient of psi 1 cross product the gradient of psi 2. It's actually going to give you alpha times a vector that's going to give you the gradient of psi 1 times the gradient, the cross product gradient of psi 2. Because you have divergence on both sides, you can basically integrate on both sides and then basically get a constant. So this is how you're getting this. So this right here, alpha can be in general a function of x, y, z, and a function of x, y, z, and time. And it's a scale, or it could, and also it's actually known as a scalar. It's a scalar because it's not a vector. Okay. So if that's the case, then what I could do over here is I could do some math here, and I could take the dot product of this, and then and we are going somewhere with all this math. There's a purpose with that. And I have psi 1 times psi 2. And if I take the dot product of that, I would get this is going to actually equal to 0, right? Because this is by definition. By definition, we define that. So one thing that we can say is that that your velocity needs to actually fulfill this criteria for to have if you had two surfaces, two streams. Okay. So that is important. The other thing that you have to keep in mind is the couple of consequences of that equation. So on any given stream, a streamline, sorry, what is true is if I take the dot of this, of the gradient, I'm going to get 0 because they're perpendicular to each other. Remember, the dot product. So if I have a vector A that's perpendicular to vector B, then the dot product of A with B is actually going to give me 0. Okay, gives me a 0 scalar by definition. So since these two are perpendicular and the same thing is true here, I can show that this is actually going to give me 0. Okay, so if this is true, well, I can say that the gradient, what we can say the gradient of psi 1 times the gradient, the cross product gradient of psi 2 is collinear with the velocity v. Uh, so in other words, what we are saying is there's nothing else than this is actually, and we already showed this previously, right? It's going to give you nothing else than a scalar times the velocity v. Now, it's important here to note that for compressible flow, if your flow, let me write this in a different color. If it's compressible, if the flow is compressible, alpha is actually equal to rho. If it's incompressible, alpha is equal to a constant. Typically, we take alpha equal to 1. Okay, that's the common value that we actually use for that. Okay, so what are some of the applications for all this, right? So some of the applications are, so let me write here, applications for a streamline function for a stream function for 2D flow. So first of all, because of vector identity, let's start with that. We know that the dot product of this with the cross product of two functions f and g, okay, they are is equal to 0. This is for any function, any type of function, f, a y, and z, and g, x, y, and z. Okay? So because of this identity, this is what we said last in the previous slide, that I'm getting this function. And this all comes from your vector calculus. Okay? So let's do a simple example. So to better understand this, a very simple example for this could be, let's consider a streamline as psi1, and it's going to be a function of x, y, and let's take a psi2 that's going to be a function of z. Okay, let's assume the flow is incompressible, take alpha equal to 1. So in that case, alpha is equal to psi1 times psi2, right? So this is equal to 1. This is equal to 1. And then this, nothing else, is actually a vector of partial of psi1 respect to x, partial of psi2 respect to x, and 0, because y, sorry, 1. Y is actually equal to that because there's only a function of x and y. The last component will be 0. In this case, it would be partial of psi respect to x is 0, partial respect to y is 0, partial respect to z is 1. So we will take the cross product of this, and the cross product will look something like this. Okay, partial of psi1 respect to x, partial of psi1 respect to y, 0, 0, 0, 1. Okay, so if you take this dot product, okay, then you will have v is equal to, remember, small u plus small v. And if I did that cross product, you can show that you get I is equal to partial of psi respect to y minus j partial of psi respect to x, and this is psi 1. Okay, that's what you actually get. So in this comparison, you see that your psi is equal to psi 1 respect to y, and your v is equal to uh, psi 1 respect to x. So, so that's how we will actually find your stream functions. So if I was going to take, just to show you, if I took the dot product of this now, right, the dot product of this, the gradient dot this, then I will get the following. Okay, it gives you partial of x of u plus partial of y respect to v, right? So if I replace these here, there's a minus sign missing there, right? If you compare this with this, a minus sign. So, and I replace this, get partial respect to x, partial psi respect to y, plus partial of y, minus partial of psi 1 respect to x. And you can see that this is actually going to give you, let me go to the next page. Partial of psi 1 x1 y minus partial of y respect to x respect to y, and that actually gives us 0. So this actually shows that this is an incompressible flow, right? Let's do another example. In this particular example, let's consider a 2D flow over an airfoil. Okay, so consider the airfoil, and you can see, let's take a stream function psi 2 and a stream function psi 1. And in this particular case, this is your axis. So if you can look at your axis, we can take psi 2 to be equal to z, any value in the z-axis only, because it goes in this z. And then your second function, so if I take the gradient of this, I will find this is equal to k. And kind of makes sense, right? But this is all I'm going to have. The gradient of this, let me show you. So let me change the colors here. The gradient of this is equal to k. So what I am saying is, if I took a normal to this surface, this is what the gradient is, okay, and that will give you the k direction. That makes sense because this is the k direction, okay. Now, so you have that, and now your psi 2, psi 1 is actually a function x1, x, y, and z, because it's a three-dimensional flow now. So for this particular case, what you're going to have is the following. So if I take V and I take the cross product of psi 1 respect to psi 2, what you will get is I, J, K. This is partial of psi 1 respect to x, partial of psi 2 respect to y, partial of psi 1 respect to z, and this is 0, 0, 1. So if I take this, you can show that alpha v will equal to alpha ui plus alpha vj, where alpha u will equal to partial of psi 1 respect to y, and alpha v is going to equal to minus psi 1 respect to x. Okay, so those will be your stream those will be your stream functions for this particular case. So if I have the stream functions, those surfaces help me to determine how is your streamline, so I know what a streamline looks like if I just took in one path. But it tells me how those lines actually go along in the three-dimensional state across the entire airfoil. So how do I know how actually the flow looks like across here? So, I don't have only this streamline. I'm going to have another streamline that actually does this. And if it's identical airfoil, all my streamlines will be completely identical. And you can see that. But now, if in the case that your airfoil is not uniform, really straight and the same as what we have in most of the cases, then you can see that the streamlines are going to actually shape what your stream looks like at every single point in the three-dimensional structure. That's why the stream functions are so important. And this is going to lead us to the conversation in our next topic of vortices and circulation. So this completes our discussion on a vortex line, vortex sheets, and tubes.